we have a mini split air conditioner PCB. I'll briefly explain the components on this PCB. Before starting, ensure you use an isolation transformer to power the PCB safely. This helps prevent electric shocks, protects testing equipment like oscilloscopes and multimeters, and ensures safe troubleshooting. So here we have a connector, which is a high-side connector, and it receives 220 volts. Then there is another connector here where 12 volts are supplied. This is possible through the transformer. This PCB is somewhat simpler compared to a typical SMPS PCB, but it's not that simple either. There are logic circuits in it, which I'll explain in more detail later. However, in comparison, it's a bit simpler. So here, when we use this transformer in place of an SMPS, what happens is that we provide 220 AC volts at this point, and 12 AC volts are supplied to the other winding. This way, the 12 volts AC come out here. And further, you'll notice there are 6 diodes installed here, whereas in a rectifier, typically only 4 diodes are used. I'll explain this in more detail later on. Each diode should be tested individually for forward and reverse bias using a multimeter. Faulty diodes can lead to partial rectification, resulting in unstable output voltages. You'll see there's a capacitor here, which is 1,000 microfarads and 25 volts. Even if a capacitor shows the correct voltage, it's important to test its ESR using an ESR meter. High ESR can cause instability in the circuit under load. You can already guess what a voltage regulator does. In this case, it's a 7805 voltage regulator. I'll explain how it works as well. After that, there's a switching relay and a capacitor here. Additionally, you'll notice the ULN 2003, which is a Darlington array. After that, there's an EEPROM and a microcontroller. Apart from these, there aren't many more components on this PCB. I'll explain their roles and functions in more detail as we move forward. In addition to that, there's a TRIAC IC for controlling the fan, which is the AQH2223. This IC is used to regulate the fan speed. Here's how it works. The microcontroller sends pulses to the Darlington array, which then passes the pulse to the TRIAC. This causes the TRIAC to open, allowing the supply to reach the fan, and the fan starts running. If the pulses are slow, the fan will rotate slowly. If the pulses are faster, the fan will run at medium speed. If the pulse is continuous, the fan will run at full speed. This is how the speed control works on this PCB. So here you can see there's a resistor, and another resistor is also present. These resistors are of maximum 51 ohms. Their purpose is to protect the fan and also to protect the voltage regulator. They help manage the current flow. However, if we look at the internal schematic, we can get a better understanding of how the circuitry works. Let's take a look at that now. So, here I have already prepared the schematic diagram for this PCB. When we supply 220 or 230 volts to the primary winding of the transformer, it steps down the voltage and provides 12 AC volts from the secondary winding. Once we have 12 volts AC, we need to convert them into DC. This is the next step in the process. But when I was showing you the PCB earlier, I mentioned that there are 6 diodes on it. Let me explain their purpose now, labeled 1, 2, 3, 4, 5, and 6. First, we'll understand the role of the 2 diodes, as that will make it easier to understand the function of the remaining 4 diodes. The 2 diodes at the bottom forms a half-wave rectifier. If we check the output using a multimeter at this point, it should measure 12 volts DC. This rectified voltage is critical for the next stages of the circuit. If any of these diodes are faulty, the 12 volts will not be generated. After that, a 4.7 kilo ohm resistor is used. When the 12 volts pass through this resistor and reach the other side, a voltage drop occurs. Due to this drop, we should measure around 4.7 volts, 4.16 volts, or 4.18 volts at this point. After that, another 4.7 kilo ohm resistor is connected further along the circuit. This causes another voltage drop. After this drop, we should measure approximately 0.667 volts at this point. The voltage becomes significantly lower. If any component in this circuit fails, the system won't function properly because the microcontroller itself won't turn on. In this system, there is a voltage detector installed here, which is a 3-volt voltage detector. It has 2 to 3 functions, which I'll explain further. One of its functions is to reset the microcontroller. The second function is to monitor the voltages continuously so that if there are any fluctuations, it can shut down the system. Without this voltage detector, the entire system would not function correctly because, as feedback, this system is constantly providing the microcontroller with information that the supply voltage is stable and there are no issues. That's why it is crucial for this component to be working correctly. Now let's talk about the next 4 diodes. The next 4 diodes form a bridge rectifier. You're probably familiar with how a bridge rectifier works, where 4 diodes are connected together to convert AC voltages into DC. Here's what happens. When 12 volts enter this bridge rectifier, the AC voltage is converted into DC. Along with that, there's a capacitor installed next, which is 1000 microfarads and has a capacity of 25 volts. At this point, we should measure around 17 volts. If the voltage here is not 17 volts, the system will not function properly. After the 17 volts come in, they pass through a 51 ohm resistor. This resistor causes a voltage drop. So after the voltage drop, we should have 13 volts DC at the output. A capacitor is also added here to control fluctuations and stabilize the voltage. So what happens is that when the 13 volts enter the 5-volt voltage regulator, the number is 7805. It will output 5 volts. These 5 volts are then used to power all the low-voltage devices in the system. When the microcontroller sends a signal to the ULN 2003, the relay will turn on because of these voltages. If the voltages are not correct, the PCB will not function properly, and the switching relay will also fail to work as expected. Now, let me show you the waves using an oscilloscope and explain how they work. Oscilloscope readings display instantaneous voltages, including fluctuations and ripple, whereas multimeters provide averaged or RMS values. Differences in readings may indicate excessive ripple voltage or a malfunctioning component. I've powered on the PCB, and the red light is visible, indicating that the system is on. The circuit board has also been switched on now. Let's quickly check the waves. If we check the waves at the 2 diodes, I've connected it here, and we can observe the full wave rectification happening. However, there's an E6 error because the fan motor is not connected. We're seeing 8 volts on the oscilloscope, while the multimeter shows 12 volts. Similarly, let's check the 4.7 kiloohms resistor. Here too, when the full wave is formed, the voltage will drop at this point. Here we're getting 2.80 volts on the oscilloscope, whereas if you check with a multimeter, you'll get 4.16 volts. This highlights a significant difference between the two testing methods. So let's check the voltage detector here. We can see that we are getting signals at this point, and these are the signals being sent digitally to the microcontroller. At this point, we are observing 2.24 volts on the oscilloscope. However, if you check with a multimeter, you'll find 336 millivolts at this point. This shows that there is a significant difference between the readings from the multimeter and the oscilloscope. In addition, if we check the high side where the bridge rectifier is located, we won't find any waveforms. Instead, we will only get DC voltages. There is a waveform appearing, and we are getting 16.6 volts. Similarly, when we check the capacitor, we are getting the same voltage there. After that, let's check the 51 ohm resistance and see the voltage across it. On the other side, when we check, we will get around 13 volts or 12 volts at maximum. Here we are getting 13.4 volts, and you can see a slight fluctuation as well. However, the PCB is working perfectly at the moment, and there are no issues with it. Now, let's check the output of the voltage regulator. When we check it, we see a stable 5 volts, specifically 4.80 volts. This shows that all the components are working properly in their respective places, and the waveforms are functioning correctly as expected at this point. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.